My name is Mitsuhisa Sato from the RIKEN Center for the Computational Science. Today, I'd like to present the design of the OpenACC compiler for the Fujitsu A64FX. So OpenACC is designed mainly for the GPU or accelerators, but my talk is about the OpenACC compiler for the many-core processors. So A64FX is a processor of the Fugaku. So Fugaku, this is a picture of the Fugaku. Fugaku is consists of the almost 160,000 the A64FX processors. So this is the block diagram of the A64FX processors. So all of you know the A64FX is the first processors ARM-based the many-core processors which have the Arm SVE. The length of the CMD is the 502 bits, and the number of cores in a chip is 48, and these are divided to the 4 groups like this. So 12 core in a cluster is called the CMG, so it's connected to the L2 cache and the HBM chips. And this chip has only HBM as a memory. So, but HBM provide a very high memory bandwidth, and totally is the almost 1 terabyte per second memory to the chip. So this is the motivation of OpenACC for the A64FX. So we want to use the OpenACC as a programming model to exploit the parallelisms of the A64FX architectures. This is the chip photograph of the A64FX. This is the ARM Intel Skylake processors. So these two chips have almost same size, 20 millimeters. That is the 400 millimeter squares. But as you see, the A64FX has the many cores compared to the Intel Skylake. So that means small core means the less output resources. So this is the comparison of the A64FX and the Skylake output resources. And also the design is relatively long pipeline, 9 cycle for the floating point operation, and the core has only L1 cache. It means that this core is high throughput but the long latency, but it may cause the pipeline stall for the long loops having the complex loop. So these characteristics of the A64FX requires more the aggressive component optimization, like a software pipelining or automatic loop efficient. So that is, the loop efficient means that we may optimizing the loop by cutting more small loops. So we expect the kernel programming or OpenACC programming may allow the more aggressive loop optimization. So again, the A64FX is the HPC-oriented design. So we expect the GPU-like coordination may improve the performance. So that is our expectation. And also, we expect the OpenACC as a programming model for the many cores wide CMD processors. It's not only the A64FX. So as you know, recent AMD, the AMD and Intel high-end processors may have the many the cores with the long CMDs. So I think OpenACC specification may provide another programming model for describe the parallelisms of the NUMA or cores and vectors more than classic OpenMP. and with separate memory management. And also many applications already ported to the OpenACC, so expect more application for our processors. So our compiler infrastructures is the Omni Compiler. The Omni Compiler is the source-to-source compilation infrastructures. So Omni OpenACC compiler already support for the CUDA code generation. Currently, we are working for the two approach for the A64FX. One approach is that using the OpenCL, and currently also we are working for the portable implementation of the OpenCL. So OpenCL may generate the code for the A64FX. And another approach is that offloaded C code and plus assembly code. This is the kind of source to transmission, and this code is compiled by the backend compiler. So today I'm going to talk about this approach. So and OpenACC has the three-level parallelisms: the GAN and workers and vectors. In case of the GPU, the GAN is associated to the SM, and worker is associated to the warp, and vector is associated in thread in warp in case of NVIDIA GPU. In case of the manycore processor A64FX, we map to the GAN to the CMG. This is the NUMA node, and the worker is the cores in in case of A64FX, and vector is SIMD vectors. And we may have the two kinds of the execution environment. So one is the execution by pthread. So the thread is used for the execute the offloaded code, and allocate the separate memory space for the offloading code, but the memory is shared by same memory space as the host code. This approach is easy to move and share the data, but it may have the side effect from the host code behavior. But another approach is that the offloaded code can be implemented by another process to invoke another process to execute the offloaded code. And the moving the data by interprocess communication mechanism like mmap or some socket or something like that. And then we may expect the process has the different operating resources such as the TLB. So we expect the more less side effect, but this approach may have the large overhead of the process switching. So this time we tested this approach. They're easy to implement. And this is the example of the translation. So this is the matrix multiplication of the non-blocking. Non-blocking is just the very conventional matrix multiplication. So this is the description of by the OpenACC, and it can be translated this code. This part is the scheduling the loop by the source transformation. But for vectorization, we are using the OpenMP the compiler as a backend compiler. And this is a version of by using the cross product. So sometimes this version may more faster than in a product version. And this is the very, very preliminary result. And the blue one is just OpenMP, and the gray one is the translated code from the OpenACC by our compiler. And the yellow one is the translated with the SIMD directives from the OpenACC. And we tested GCC and Fujitsu compiler. And so in most cases, performance is almost same. So it's a little bit disappointed. And no performance improvement. The OpenMP OpenMP compiler. But as you can see, some cases that by the translation from the OpenACC may increase the performance like this. And this is the result of LLVM. So, and as you can see in the previous slide, some improvement were found in the Fujitsu compiler, so like here and here. So the execution by process can be extended to execution by another node like this. This is the one node, the execution by the process, but it can be extended by another node like this. It is useful for exploiting another parallelisms, but in this case, to make it efficient, we need a kind of asynchronous offloading. But the basic question in Fugaku is that it's made better than the old process used in MPI process. We need to explore this kind of things. So currently, we are working on an OpenACC compiler for the A64FX. This is a very preliminary and alpha version, and several design choices were exist, such as the code generation and the execution environment. But we expect the OpenACC programming model provide another possibility to exploit the parallelisms, the manycore SIMD, the processes using NUMA and cores and vector parallelisms. And this expectation can be applied to the recent high-end the processor at the AMD. And the preliminary still need to examine. So we're just using the implementation by the thread and some very easy the simple loop transformation. But we need to examine the more complex loop by the OpenACC, and also we should test in another implementation of the execution environment by the process. And a different path is that using the OpenCL. So if OpenCL enables the more aggressive optimization, I think this is another way to exploit the parallelisms of our A64FX processors. And currently, we are working on porting the POCL, the OpenCL, compiler to the A64FX. And finally, I know that the GCC is already support the A64FX, and the GCC is also can generate the code for A64FX. I tested by GCC OpenMP or A64FX, but the performance is very disappointed. We need to explore why this GCC of the OpenACC is so slow. So thank you for your attention.